So, how do you measure something you can't actually see or touch? Sounds kind of impossible, right? Well, today we're tackling a classic physics puzzle that's just like that. We're going to find the focal length of a convex mirror, and it's going to take a little bit of optical magic to pull it off.
Okay, so here's the core of the problem. A convex mirror, the kind that bulges out, creates what we call a virtual image. The image literally forms behind the mirror in a place where light rays don't actually go. It's like an illusion. You can't project it on a wall, so how on earth are you supposed to measure it?
Right, and because you can't project it, you can't just stick a ruler there and get a number. That's the puzzle. But, and this is the really cool part, there is an incredibly clever workaround, and we are going to walk through it together step by step. So here's our game plan. First, we'll dive deep into the puzzle itself. Then, we'll introduce our secret weapon, a convex lens. After that, we'll show you how to set up the whole experiment on an optical stage, master a really cool technique called the no parallax trick, and then we'll run the numbers to get from R to F. And finally, we'll talk about why this isn't just a lab experiment, but something that actually matters.
All right, let's get right into it. What is it about convex mirrors that makes them so tricky? Well, it all comes down to the way they play with light.
So, a convex mirror bulges outwards. Think of the back of a spoon. When light rays hit that curved surface, they spread out. They diverge. Now, our brains are pretty smart, and they trace those scattered rays back to a point that looks like it's behind the mirror. That imaginary point is the principal focus, F. But here's the catch. The light isn't really there. That's why we call the image it forms virtual. So how do we get around this whole virtual problem? Well, you fight virtual with something real. And to do that, we need to bring in the hero of our experiment, the convex lens. A convex lens is basically the opposite of our mirror. It's thicker in the middle, kind of like a magnifying glass, and it bends light rays inward, forcing them to converge at a single point. And this is its superpower. It can take light from an object and form a real, physical image, one that you can actually project and pinpoint in space. This is the absolute key that unlocks this entire puzzle. So here's our first move. We take an object, let's call it O, and we use our convex lens L to create a sharp, real image at a point we'll call I. The most important thing here is that we've just created a tangible, measurable point in space that we can actually work with. It's our anchor.
Now that we've got our key players, we need to arrange them. And to do that, we use something called an optical bench. You can think of it as just a long, straight rail that makes sure everything stays perfectly lined up. For this, we're going to use a special 4-upright setup.
So what's on the equipment list? Well, we've got our optical bench with 4 stands. We need our convex lens and, of course, our convex mirror. We're also going to use 2 optical needles. These are basically just sharp pins on a stand. One will be our object, and the other will help us find the image. And finally, we need holders to keep our lens and mirror steady. Putting it all together is pretty logical. First, you set up the object needle, O, at one end. Then, a bit farther down, you place the convex lens, L. Third, you look through the lens and find the exact spot where it forms a sharp image, and you put your image needle, I, right there. And then, here's the crucial move. You slide the convex mirror, M, into the space between the lens and the image needle. All right, this next part is where the real magic happens. The second you put that mirror in place, that original image you found, well, it vanishes. So what now? Now we use a really neat technique called the no parallax trick to find the mirror's center of curvature. The entire method hinges on one beautiful principle of optics. If a light ray hits the surface of a spherical mirror along a line that points straight to its center, it will reflect and go straight back along the exact same path. It's like a perfect optical U-turn. So our job is to adjust that mirror M back and forth until the light rays coming from the lens hit it perfectly head-on. When we get it just right, those rays do that perfect U-turn, travel back through the lens, and form a new image right on top of our original object needle, O. And this can only happen if our image needle, I, is sitting at the mirror's exact center of curvature, C. So how do you know you've found that perfect spot? By eliminating parallax. You look at the object needle and its new reflected image, and you move your head from side to side. If they seem to shift and separate, you're not there yet. You keep adjusting the mirror until they move together as one, like they're glued together. When that happens, you know you've absolutely nailed the position. And just like that, we've got our unmeasurable value. The distance from the surface of the mirror to the position of our image needle, I, is the radius of curvature, which we call r. We've just turned a tricky optical puzzle into a simple distance we can measure right there on the bench.
So we've done all the hard work. We used a lens and a clever trick to measure the radius of curvature, r. You'll be happy to know that the final step, to get the focal length, f, is actually refreshingly simple.
For spherical mirrors, the physics gives us this beautiful, direct relationship. The focal length, f, is simply half of the radius of curvature, r. All that setup, all that careful adjustment, and it all boils down to one easy division.
Now, in a real experiment, you'd never rely on just one measurement. You always repeat the process a few times to make sure you're accurate. So here's the table with some sample data. You can see that for different setups, we get slightly different values for r. That's totally normal. So we just take the average, the mean, to get our best possible estimate. In this case, it's 13.8 centimeters.
And here it is, our final answer. We take that mean r value, 13.8 centimeters, we divide it by 2, and we get our result. The focal length of our once unmeasurable convex mirror is 6.9 centimeters.
So that was a fantastic walkthrough of a classic experiment. But let's be honest, why is any of this important? Where do we actually see these things in action, out in the real world?
Well, the truth is they're everywhere. That side view mirror on your car, the one that says objects in mirror are closer than they appear, that's a convex mirror. It's designed that way to give you a much wider field of view so you can see your blind spots. You'll also spot them in parking garages and in the corners of stores as security mirrors for the exact same reason. They let you see a huge area in one tiny reflection.
You know, we started with a puzzle, a property we couldn't measure directly, and we solved it by using another tool to create a situation that we could measure. This whole process of indirect measurement is really at the heart of so much scientific discovery. It kind of makes you wonder, right? What other things that seem totally unmeasurable today are just out there, waiting for the right bit of ingenuity to finally be revealed?